happening in the atmospheres that we just literally didn't think we'd be able to see them with JWST. Even though we knew it'd be a great telescope, it was still just that much better than expected. And we're so excited. I mean, even these initial detections that we're making, they're already rewriting the textbooks for our understanding of the composition, like going from galaxies and formation timescales to exoplanet information and solar system. In every scale, we are rewriting textbooks like every day.
And I'm curious, what was it like? What was the feeling that you had when you saw that first Webb image? Stephanie?
So for me, one of the first images that I got to see was obviously the Carina Nebula, and this is just one of the most breathtaking image, I would argue, that we've had to date. We can argue about that later, Nicole. But it's spectacular in every form, and it's artistic. It is beautiful, but it's also just bursting with science and discovery. Also, if it's not your background of your phone or your computer screen, you clearly have not been paying attention. But at any rate, so what we're learning about, even when this first image came in, so beyond its beauty, I had to take a moment and I had to pause, because already I could see the discovery space just coming out of this. The science, we were told we weren't allowed to science the images that were being released in the first set of images. And it was so hard to sit there and keep your mouth shut about all the things that we can see already, the discovery space, the new ways that we can see star formation and planet formation happening. It's like happening in this picture. And it was an emotional experience, the culmination of, the multiple decades of people working together to build this telescope, the 6 months of day in and day out commissioning, waiting for these images to be released. It was a lot of energy, and it was just a lot of relief, and it was a lot of excitement. So I'm just excited for more to happen.
Anyone else? Any thoughts you had? Go ahead.
Very similarly. So for me, my first image was when we were, launched. I started to switch on the instruments, switch on the detectors, and you start to get these first engineering images that obviously are not as beautiful as this one, but they already indicated how well everything was working. And then at some point, there was all the work of making all the mirrors, the segmented mirrors, to work as a single one. And I'm sure you all saw that first sort of, again, engineering image showing a very bright, sharp star in the center, which was like, it is working so well, and it's really going beyond expectations. But also you could see around all these little tiny galaxies that personally, I didn't expect to be so many of them. Like Peter and I, we started to call the photobombing galaxies, and really, it's all about, often we were thinking, like in preparation for commissioning, we need to observe an isolated galaxy to do this or that. There are no isolated stars with Webb. Everything is surrounded by galaxies and by more sources that are out there, and we need to explore. So it was a great experience, and of course, the culmination, as Stephanie was saying, was this beautiful set of images that was released for the public to enjoy and to really see why it was worth it, but also for the community, the scientific community, to really dig into data and start making science and start taking advantage and learning about a new mission, a new telescope that we launched last year. So yeah, it was very good.
And Nicole, how did that moment make you feel?
I mean, it's similar to what's been said. Literally these pictures are full of just unimagined detail. If you download the high-res versions, you can zoom and scroll for days, and discover new features. And it's incredible to know that in these first images alone, it's only the beginning, and we're already seeing evidence of new stars forming, galaxies everywhere, baby planets that could be forming. And it was just unreal and, very humbling that, we all did get to take part in this amazing journey to help get those images out to the public last summer. And we were all involved in the 6-month commissioning, like around the clock work as well, just to get these ready. It was a lot of hard work, but it was so worth it. And, it's just, yeah, you almost have no words to describe.
And Amber, what was going through your head during that moment?
Yeah, I mean, similarly, I think one of the most fun parts was just being the part of the like behind the scenes team that was getting the telescope ready for, for its public debut. But we got to see the engineering images that came through during that 6-month commissioning period, which was a very intense time of getting the telescope ready for operations. And so for me, being part of that team that was working together to get the telescope working was really incredible. And then, when we released these first images, it's just, from a scientific standpoint, like Stephanie was saying, you could see the richness, you could see the detail, the things we'd never seen before. But on a more human level, I think for me, it was good to just to sort of step back from my scientist persona and just take in the beauty of these images. They're beautiful on a deep human level. And so for me, it was emotional. I think a lot of us were like, we all cried when we saw the images the first time. They're undoubtedly very beautiful.
Tell me a little bit more of some of the other new discoveries that we've been seeing.
So beyond, the farthest galaxies and, planets around other stars and exploring our solar system, one area that we're really getting a lot of new information and already a lot of science out of is the birth of stars. So understanding star formation in a way that we've never really had access to. We don't know how massive stars are formed. We don't know how small stars or binary stars. We don't know how all these complex new planetary systems we're now seeing, how they're formed. And when we look inside these giant clouds of gas and dust, we're seeing that dynamic actually happening. We can study the chemistry, we can study the physics, and again, it's just with this whole new sensitivity and detail that we've never had before. Not only are we studying star formation in our own galaxy, but even in other galaxies. So even what we're seeing here in the Cartwheel image, we're seeing these galaxies are colliding, but it's also triggering all kinds of new stars to be born and formed. And we're getting this detail now that we used to only have on our own galactic understanding, now expanding into these other galaxies across the universe. And it's just really an exciting time to be part of that field and understand how our sun was born and how the solar system was formed. And this is giving us that first real glimpse of it.
And when it comes to galaxies, what more are we learning here?
Well, with JWST, the thing is that many of these galaxies, like the Cartwheel that you can see now on the screen, they are close. So you would think, well, is it quote unquote worth observing it with Webb? And the answer is absolutely yes, because we are seeing it so much detail and in-depth studies. So in this case, for instance, you see how this galaxy has this very strange shape, like a wheel. And this is because it did undergo many years ago a very strong and fast collision, essentially, with a smaller galaxy that sort of went through and created those spokes that were originally the spiral arms of the first galaxy. So what we can see studying galaxies is we do have at hand the perfect laboratory to study with JWST how galaxies form, evolve, and essentially how to start forming inside. You have to put together all that information from the detailed studies from the solar system, from the solar system to the nearby stellar forming regions in our galaxy, and then extrapolate those to galaxies. And then you have to put together the environment. How do forming stars affect the environment? It creates filaments, it creates new stars, they evolve into supernovas. We can start studying, we do study materials that are essential for the formation of both stars and planets. And at the core of the galaxies, we do have the supermassive black holes that they have a very intimate interplay with their environment. And in many cases, they are, if the nucleus is active, they shine so bright that it literally outshines the whole stellar emission of the galaxy. So there are many advantages to study galaxies, because when you understand your local galaxies, you can then say, okay, now let's see if this model we have in mind fits to all the galaxies in time. So it's really putting together many pieces of the puzzle with detail never seen before in the infrared.
Absolutely. And one thing that really strikes me with these images is how much they inspire us all to wonder. And really, there's an explorer at the heart of everyone. And these images have allowed us to really explore the unknown together. Why do you feel like this is so important, Amber, and why is this so inspirational?
Well, I think one of the main reasons it's important is that JWST shows us that we can do, very difficult, big, bold, almost impossible things when we're all working together for something good. And I think astronomy is good. I think in a real sense, we're living in a difficult time right now as a world, as a species. And for me, last summer, I feel like releasing those images was like this breath of fresh air. It was something good. And I think that these telescopes are something good that we can do for the world. And as far as inspiration goes, one of the things I love most about astronomy in general is that astronomy gets to the heart of our big questions. Where do we come from and how do we get here and are we alone? Those big questions that are more than just arcane science questions. They're questions that get to the heart of what it means to be human. And I think all of us have the common experience of looking up at a dark night sky and just sort of intuitively asking those big questions. And I think these telescopes help push us forward in understanding more about our world. It's a fundamental part of being a human being is to explore and discover, and they help us with that.
And building the mission, launching it, and commissioning it has been a hugely international project. This is such a feat. How's that been for you to collaborate to make this happen? Maka?
For me, it's been the best part of the experience. So my whole career has been based on web, essentially, JWST, working in different places, different capacities, but all the way through, for me, the best part of it was getting together with a team, working the problem, seeing what to do next, and really planning to have this amazing telescope we have out. And I want to echo Amber, essentially, this really shows how we are all at our best when you put all our brains and all our effort together to do something this spectacular. So it's been a gift, personally, to be able to be part of this team and to enjoy it.
Thanks. Stephanie, what's been the most rewarding part of this awe-inspiring project for you?
There's so many to choose from. I think it's probably been the most rewarding getting to work as part of this huge team. 20,000 people, over 2 decades. I've been on the project just barely over 10 years, and what I've learned from those individuals that have been working on this for almost 30 years, I gained so much information, insight, knowledge, and it has been fantastic to be part of this huge team and watch how they've worked together, work through our issues, our challenges, and deliver the best infrared space telescope that we ever had.
Thanks. Now let's go back to those challenges. So to get to this point, you probably faced a lot of challenges, and I just am curious, were there any role models that you felt helped you get to this point? Nicole?
Yeah, I'll start by saying, my parents are huge role models. They are not scientists. They are not involved with the James Webb Space Telescope, but they always have had and still have, an amazing work ethic. And that is part of it, perseverance, basically, to get through challenges. And I can speak to my personal experience. The project, it had a lot of challenges over time. But I was relatively new to the project, joining in late 2019. And, if you might recall what happened a few months later, a pandemic started. And, it was hard to get caught up in all of those, with the decades of experience. It was very humbling and a great challenge, but still an exciting challenge. Amber was saying, it's worth it, to be able to share and to get this telescope out to share the universe with the world. And so a lot of, nobody said anything in particular to me, I guess. I will say our team was very supportive overall, so it was really great to be able to work with, be one of 20,000 people working on the project and even playing a tiny role to help get this mission where it is today. But, I definitely have my parents to thank over the years. They never gave up on me or my siblings, and that really helped push us along. And just to add one more thing, I never did the best in school. I didn't have the greatest grades at times. I had professors say they were literally disappointed in me, and I'm like, but you know what? I can do it, right? If I knew I wanted to work at NASA one day, I was going to make it happen. And so it's all about perseverance and overcoming these major challenges. So for me personally, but also I think that's a good theme for the project as a whole, everybody working together to get through various obstacles that we had, including launching during a pandemic. Yeah.
Thank you. And for you, Amber?
Yeah, so challenges. I mean, yeah, I grew up in rural Arkansas, and so I was not surrounded by a lot of scientists. But similar to Nicole, my parents were huge supporters. My mom was always like my biggest cheerleader. But yeah, there were definitely challenges to growing up, in a place where there wasn't a lot of, actual, real life scientist role models. But parents were supportive, and I grew up during the shuttle program at NASA. And I was in the 5th grade when Hubble launched, and all of that stuff happening at NASA in my childhood made me really want to be a part of it. And a definite upside of growing up where I did was the sky was dark, beautiful and dark, and that's how I got into astronomy to begin with. And so. Yeah, similarly to Nicole, I had my own challenges, getting through school. I failed my big physics test to get my PhD the first time. I had to take it again, We have all these silly mantras like failure is not an option, but, that's not true. Failure happens. When you're doing hard things, you're gonna have moments of failure, and I think that's true personally. It's definitely been true in this project. We had engineering setbacks, but we figured them out, we persevered, we got it in space, and now it's working better than we ever expected.
And what was the big driver for you in your career, Maka? Like what really inspires you about being a scientist?
Personally, I get what drives me daily, it's the challenge itself, the problem solving. We are all problem solvers. We like to take something hard, as Amber was saying, and try to see how to either understand it or solve it if it's an issue. So personally, it's all about, we have this observation that doesn't fit theory, then you have to go back to your drawing board and really try to understand what is going on. We have some technical issue with whatever part of the integration of the telescope, then you have to go back, figure it out, and solve it. So it's all that constant, interesting process. It's really a scientific process that I really enjoy, and I feel that's my driver. It really makes life very interesting. And the 4 of us could see the same problem exactly in 4 different ways, and probably by talking to each other would find like a perfect solution for that. So it's great. Problem solving and collaboration.
Thank you. And what are you most looking forward to, Stephanie?
The unknown. Every time we look at one of these fantastic new images, spectra or otherwise, we're seeing things that we've never seen before. And that's bringing out the curiosity and the challenges that we have as scientists to say, why did that happen? How did that happen? What's making that happen? What's the evolution of this process? And what can we learn from it? And every time we do that, and we've been doing this for, hundreds of years as astronomers, as scientists, as humans, every time we look and we have a curiosity about something, we look harder. And I think this first couple of years of science with JWST is going to open the door to huge new questions and challenges that we have ahead of us on, the evolution of the galaxy, whether or not there could be life on another planet, whether there's life in the solar system. All of these things are challenges that are put forward to us, and we're doing the best that we can, but sometimes we think that we can do it better. So we build bigger and better telescopes. We collaborate with international teams, because sometimes these projects are bigger than just one person. And I think the new discoveries, the unknown unknowns, is what I'm the most excited about with Webb.
Would you like to add to that, Nicole?
Yeah, it's been, less than a year, of science, and every image, every spectrum that we're getting, it's just changing the way we view the universe because it's revealing new information. And a lot of what I study involves exoplanets, these distant worlds outside the solar system. And, a lot of what I've talked about today and mentioned today was these gas giant like Jupiter-sized planets that we've been studying, but there are many smaller rocky planets that we are looking to study with JWST. It's already studying some of these, and I'm excited to see, you know, what we learn about those planets that are around the same size as our own. You know, they might not always be the same temperature, you know, they might not have surfaces with liquid oceans and all that, but we expect to still learn about their overall atmosphere and, you know, is there water in the atmosphere? Is there carbon dioxide? Is there anything familiar to us that we can connect to and relate to help us understand better of, you know, is there other life out there? You know, what can JWST reveal? And it's also helping set the stage for future NASA goals as well.
And this telescope really belongs to the world. Could you tell me a little bit more, Amber, about who's using this and like how this is for everyone?
Yeah, I think you mentioned, Laura, in your introduction that this telescope was the result of 14 different countries working together. So engineers from, you know, all over the world built it, and an even larger number of astronomers from all over the world are already using its data. But I think, you know, beyond the engineers and the scientists that actively use the telescope and built the telescope, it really is for all of us. I think astronomy is for all of us, and these beautiful images, they're all, by the way, freely available online. You can go download all of them, and I think it really does show that these beautiful images in astronomy are here to inspire us to think outside of ourselves and to think bigger.
Thank you so much. I really am so appreciative of you all being here today, and now we're going to take some questions. So here we go. Oh, this is a great question. Is there extraterrestrial intelligent life? I want to believe. Max Peng.
Do you want me to? I could
Go for
it. Sorry. Yeah, I was just talking about, you know, the potential for JWST to at least study rocky, you know, Earth-sized planets. But is there actually extraterrestrial intelligent life? There could be life. Is it intelligent? You know, is there intelligent life on Earth? No. I guess it depends on, you know, the how you define intelligent, but I think I want to believe too, I guess, is the bottom line. There's billions of stars out there, which means there are billions of planets. So, you know, in a more serious answer, I think there just has to be, you know, otherwise, again, a Carl Sagan quote, like, it's a waste of space if humans are the only intelligent life in the universe.
Thank you. Another question, how long does it take to plan, position, and take a single photo? Peter Dwyer, thanks for that question. Maka? Yeah, thanks.
Well, like everything, it depends. Typically, all the data that is taken in a year, all the scientific programs are prepared by the, you know, scientific community. They send their proposals and they get approved. So that preparation takes place perhaps a year or more than the observation is taking. So when it's approved, it goes into the scheduling, and say your observation is going to happen tomorrow. So depending on the object and depending on how bright or how faint it is, it can take any time from, you know, 1 hour to tens of hours. It really depends on what you're seeing. If you are interested in solar system targets like Stephanie, it'll take typically half an hour to get to your target from, you know, when it's planned, and very little time to get a very sharp image. But and then you have to, if the source is very big, you have to, you know, do many shots and do like a mosaic. But yeah, it's a very sensitive telescope, but it really depends on what you're looking at.
I think one of the, just to add on to that, one of the awesome things about this telescope is how sensitive it is, how efficient it is. So, you know, we had these beautiful deep fields from Hubble, like the Hubble Ultra Deep Field. And if you look at those images from Hubble, which are beautiful and taught us incredible things about the universe, they took days, 14, 20 days of observing. And we saw in that very first image that we released last summer of the deep field that we got an image that was even deeper in the infrared in just hours of time. And so really the power of this telescope is how efficient it is in its observational capabilities.
Thanks. We have another question from Colleen Berg. What do you mean by the colors we choose to depict? Can you expand on that process, and why don't we see it as it is?
I can take this one. So, as was explained, we have an infrared telescope and not a telescope that operates at wavelengths of light that you can see, so visible light, the way the Hubble telescope does. So in order for us to understand and study any of these given objects at these longer wavelengths of light, which our eyes are not sensitive to, we hone in on colors and we label those colors as to define a given physical process or chemical process, so that we can study those details in ways that our eyes can actually see. Because when these images come in, they're black and white. It's a series of ones and zeros, lots of pixels, and we take a picture with a given filter, and we take another picture of the same spot with another filter. And we just color one filter green, one filter red, one filter blue, and each of those filters are telling us something different about that object. And we just give them those colors based on, we try to follow the same color coordination as visible light, so longer wavelengths we tend to color more red, shorter wavelengths we tend to color more blue. But it doesn't necessarily have to be that way. It's just a way that we try to standardize when we make these beautiful images that you see here. But if I was looking at an object in the solar system, I might choose different colors just to highlight certain types of phenomena that are happening in Jupiter's atmosphere, for example. I could totally label the Great Red Spot as red in that image, but there's other things, there's other dynamic processes happening in Jupiter, for example, that we wanted to emphasize, and that's why those filters were chosen and those colors were chosen.
Thanks. And another question very similar from Hi Nukin. How does the team decide where to point the telescope? Anybody? Go ahead.
Yeah. So the team doesn't decide where to point the telescope, essentially. This is a telescope for the world. So the way it works right now, after we did commissioning, and that the team decided because it was all about, setting the instruments and really demonstrated we could do the science. But now for science operations, the way it works is that once a year, typically there is a call for proposals. And the entire scientific community is invited to send their ideas. You could send, I want to use this instrument, I will serve this target, and this is the science I want to achieve. And then all those proposals, and this year, it was closed recently, and we received like 1,700, 1,600, a lot of proposals. So this will be reviewed by several panels of experts in all the different scientific topics. And it's an interesting process because it is double blind. So the reviewer doesn't know who is submitting the proposal or which team is submitting it, which is really great because it removes a lot of biases. So the panels decide and they rank the proposals, and the top ones are the ones that make it into the schedule. But it's all merit-based, and scientifically interesting proposals are the ones that are chosen.
And I think even one of the awesome things about these telescopes, and I think a lot of people maybe don't realize, is that, an astronomer, say they were one of the lucky ones that got their awesome proposal awarded. And so it depends on the program, but typically that astronomer and their team will get a year with the data. But then after a year, the data is public to everybody.
Absolutely.
And a lot of the programs, especially during this first year of operations, have no proprietary period. So that means as soon as the data is downloaded to the telescope and in the world, it's in the world for everybody. Anyone can use it. And a lot of the early teams have made the choice, the solar system team decided, we could keep this data, but we're going to make it public for everyone so we can learn as much as we can about the telescope, how it's operating, and about the science. And that's another sense in which these telescopes really are for the entire world.
Thanks. And Carly Free has a question. Any clues as to what space is telling us about the future of Earth?
Oh. Yeah, that's a broader question. I mean, it could be James Webb specific. But that's a really good question. I mean, there's different ways that we're studying planets, including everything in our solar system, as well as asteroids, comets, like the building blocks of our solar system. And then we're studying over 5,000 exoplanets that are ranging anything from similar in size to Earth to Jupiter size. So we have a great sample that continues to increase as we're studying exoplanets. And what we do want to do is compare those systems and say, do they have any similarities to Earth? What is their relation? I mean, Earth is like a middle-aged star. Our sun is a middle-aged star, so Earth is a middle-aged planet, if you will. And we are studying planets that are around younger stars and around some older stars too. So I think we're still very much in the early days of deciphering all the exoplanet data to see, okay, could any of them be like a future Earth, right? But I will say Mars is a great example of, closer to home that maybe Stephanie, you want to elaborate on as a potential way that Earth could evolve in the future.
Yeah, I can add a few thoughts on that as well. So our Earth has looked very different. So if we had the James Webb Space Telescope when the sun was formed and the planets were formed in our solar system, if we were looking at our solar system, the Earth back then in the early days looked very, very different from what it looks like today, and it has evolved and changed dramatically during the evolution of our solar system. You can think about the heavy bombardment era where everything just kind of got blown off of the surface of the Earth. Even before the first signs of life, we had very different atmosphere. So while Nicole's studying planets around other stars and studying their atmospheres, who's to say that that planet's not going to evolve to something like what Earth looks like today? We're getting these instantaneous snapshots of things that happened billions of years ago sometimes, or hundreds of thousands of years ago. So who knows what they are today in real time? We can look at our history, we can look at other planets in our solar system and see how they've been impacted by their own evolution, Mars being a fantastic example. Once having huge oceans and lakes, we see that with the rocks on Mars. We see, riverbed-like rocks that are rounded from processing of liquid water flowing on the surface. These are things that give us all the clues of how our planet might actually evolve. And if we don't take care of it, we might have a lot more detrimental effects sooner than later.
Thanks. And Louise Pershini asks, how can James Webb help us advance the understanding of cutting-edge mysteries like dark matter, dark energy, etc.?
So Louise knows his astrophysics. Good job. Yeah, I guess again to zoom out. So we think that about 75% of the whole energy matter content of the universe is this mysterious thing that we call dark energy. And another 20% is this other mysterious stuff called dark matter. So you're noticing a trend here, right? When astronomers don't know what something is, we label it dark. But it's astounding. So all of these things we've been discussing today, the hundreds of billions of galaxies and the trillions of stars and countless planets, all of that only makes up about 5% of the whole universe. And the rest, the other 95%, we don't know what it is. And so there are ways that JWST is going to help us in learning specifically about dark matter, because you can sort of think of dark matter as the scaffolding of the universe. It's the scaffolding on which the galaxies sit. And so by studying how galaxies evolve over time, we're able to learn more about how dark matter behaves. And so in that sense of studying how galaxies change over time, we can learn more about dark matter. Dark energy, we can also study dark energy with JWST in some of the similar ways we've done so with Hubble. But we're actually building another telescope that's going to launch in 2027 called the Nancy Grace Roman Space Telescope. And we're already building it, already testing it. Things are going great. And that particular telescope is specifically designed to study dark energy. So we should be learning a lot more about dark energy later on down the road with the Nancy Grace Roman Space Telescope.
Thanks. And David Frager asks, what is the expected lifespan of Webb?
Stephanie?
Oh, sure. So we built this telescope with a requirement. So NASA had to deliver a space infrared telescope that worked for 5 years. We also were told that we had to carry about 10 years worth of fuel. We do have a fuel limited mission as we were launching. That was our plan, was once we ran out of fuel to maintain where we are 1 million miles away from Earth and to unload momentum, that would be the end of mission. Fortunately, because of our fantastic colleagues who helped us launch our telescope into space on an Ariane 5 rocket, we had such a nominal launch. Nominal just doesn't say the words. It was absolutely flawless. Our launch was so perfect, you could not see the error bars in what we hoped to do versus what we actually did. And even in our first images that we had of the telescope, once it detached from the spacecraft and started drifting on its journey, we saw our first deployment happen. We saw the solar array unfold, which meant the launch was so perfect, we didn't even have to tweak which way the telescope was pointing. It was already pointing in the right direction, already going on its journey, and it automatically started deploying itself because it knew that everything was perfect. So our calculations after our launch, after our insertion into the orbit that we're in, gave us estimates of 20 years of science mission lifetime, which is fantastic for the next generation. Fingers crossed all the instruments work that long. Fingers crossed, we don't have any other major setbacks with the observatory. I mean, we have a giant sun shield that's made out of basically happy birthday balloons. So, we are a little fragile. But we're doing the best we can to maintain and operate our telescope in a safe way so that we will have science for many decades. So,
thanks. And Anonymous asks, what's been the most wow moment in each of your careers so far? P.S. Love seeing an all-woman panel for a hardcore STEM topic. Girls, get it done.
I mean, I could start by saying this is the most wow moment. Honestly, I think it's hard because working at NASA is just a lot of fun, and we do get a lot of wow moments. Like, I'm very grateful for that in the sense that we get to work on all kinds of really amazing space missions and get them out to the public so that we can share these incredible data with you and explore the universe together. So in a way, almost every day is a wow moment when we're working on these missions, so that's not really, one single moment, but I feel like there's so many, it's hard to pick one.
Anybody else want to add anything?
I can pick one.
No, sure.
So for me, my wow moment was definitely the day of launch. Like, there was so much at stake, so many years, so much effort that has put into that, so many dreams and hopes into that mission, that it was really fantastic to see it so nominal and boring, quote unquote. It was perfect, and it was a very enjoyable moment, and I really treasure that. And then, of course, everything after it. Nicole is right. We are lucky, and there are many great moments, but for me personally, the day of launch was fantastic, really.
I think we have time for a couple more questions. Al Conde writes, NASA science is rewriting science books at an increasing and accelerating rate, a good problem. Is the agency exploring new ways to disseminate all this?
Amber?
Sure, yeah. I mean, NASA really takes seriously, I think, its role to explain what we're doing to the public. And I think, all of us that are involved in these missions really try hard to do that. I mean, this is a good example of one of the ways that we try to do that. But yeah, the agency is always trying to think of new ways to, to get our information and our data out to the rest of the world. I think it's forward-looking in a lot of ways. NASA was one of the first, maybe the first government agency to really embrace social media, and so I think that there's a lot that our communications teams do, which Laura is a part of. Thank you, Laura. That our communications teams are fantastic and work really, really hard at making sure that we can make the science understandable and get it out to the world.
Thanks. And let's see. Here we go. No, new question. What kinds of discoveries are we hoping to see in the next couple months?
All the things.
Too many.
So I can say we have a lot of fantastic work that's coming out from the telescope. Now that we're just sort of almost finished with our first year of science operations, the science community is really working hard on analyzing their own data and putting it into scientific peer-reviewed publication, the way that we are supposed to do and we get paid to do. And so that is now finally coming out and it's coming to fruition. So lots of science is coming out in the literature that's come from the James Webb Space Telescope. We have a queue of how many press releases for future publications that are coming out. So it is a very exciting time. Amber and I get a lot of the behind the scenes looks at some of those things, and just seeing the new science and the new discoveries on the horizon. Just stay tuned. I mean, every week we release something, so just follow us and I'm sure you'll be astounded.
And I want to thank you all so much for being here today and for everyone following along. And thank you. And if you want to follow along for more updates on NASA's James Webb Space Telescope, check out our social media at NASA Webb. Thank you so much.
We are going. The history of this agency is marked with broken barriers, once viewed as impossible, with science fiction turned reality, with innovations that have spun industries all their own, and with demonstrations